To begin, I ask you kindly to switch off your microphones except for the speaker. So you are welcome.
Thank you. First of all, I want to thank you for the invitation to talk at this seminar. The title of my talk is Non-Local Symmetry of Complex Monge-Ampere Equation Generates Anti-Self-Dual Ricci-flat Metric with no killing vectors. This is the outline, but I will skip it and go just to the material. First of all, something about Einstein equations. The unknown thing there is the metric. It could be...
Excuse me, please. Can you make full screen?
To make which screen?
Full screen.
Full screen?
Yes, Control L.
Control
L.
L?
Mm-hmm.
Like this?
Oh, yes, much better. Thank you.
Okay, I am a new one with this technique, you know.
Yeah, it's much better, okay.
So this is the metric, and E, A, E, B, this is the vectors of the tetrad, moving tetrad, which moving frame, which the metric in this moving basis is just trivial, just either 4 pluses or 2 pluses, 2 minuses. The first is the Euclidean signature. The second one we call ultra-hyperbolic or neutral signature. Okay, now I don't see how to... like this. Now, what is Levi-Civita connection? It is defined by one forms omega AB, and this is the first set of the Cartan structure equations. Now, using the connection, we can define also curvature 2 form RAB like this. This is wedge, you probably know. And the important thing is, this is the relation between the usual tensor notation and differential forms notation. And the important thing is RABCD is the curvature tensor. And this is RAB, what is called Ricci tensor. And it is important because empty space Einstein equations with zero cosmological constant read like RAB equals 0, which we say that the metric which is the solution of these equations is Ricci-flat. If the whole curvature tensor vanishes, then this is just uninteresting, trivial case of flat metric. But when only the Ricci tensor vanishes, It is not trivial. We call it Ricci-flat, and this is a solution of Einstein equations. Now, just to understand the starting point, let us recall what is the so-called Hodge-star duality transformation. It maps in the n-dimensional manifold, it maps P forms into n minus P forms. And we can extend this definition to the duality transformation of forms of curvature 2 form, of curvature tensor. And now, when we have in 4-dimensional space, when we have Euclidean signature or neutral signature, then why these cases are so important? Because under the duality transformation, two forms are mapped again into two forms. Therefore, we can define self-dual forms or anti-self-dual forms. And anti-self-dual is more popular with the British school of Cambridge and Oxford University, so I will speak about anti-self-dual, though it is not important which case I choose. Now, the history of the subject starts with Plebansky, who published in 1975 in Journal of Mathematical Physics his pioneer paper, where he showed that if you consider space with either Euclidean or neutral signature, then the whole set of complicated partial differential Einstein equations reduces to just one equation, which is the complex Monge-Ampere equation. The metric becomes Keller metric. The metric coefficients are just mixed derivatives of the single Keller potential U, which depends on two complex variables and two their conjugates. And the complex Monge-Ampere equation has its right-hand side either +1 for the Euclidean signature or -1 for the neutral signature. And the result is that any solution of the complex Monge-Ampere equation for U yields the metric defined in the formula 1, which automatically satisfies all Einstein equations, which means that this metric is Ricci-flat. Now, of course, you may ask why such signatures, they are unphysical, because the physical signature is minus plus plus plus, Minkowski signature. And but as I explained, it is well, impossible to impose the condition of self-duality or anti-self-duality. Then you may ask, why, what to do with this unphysical metric? The answer, unphysical signature, the answer is that the hopes are that in the future quantum theory of gravitation metrics with such unphysical signature will influence the physical world by some under-barrier transitions which are allowed in quantum theory. So it seems like that the most elegant mathematics, the most elegant picture is hidden behind the scene, and it should influence somehow on our observable world. Now, introduce the coframe of one forms in which the metric takes the canonical form. Omega 1 times omega 1 bar plus epsilon omega 2 times omega 2 bar, which makes obvious the claim about the signature of the metric, either Euclidean or hyperbolic. And this formula 4 is valid for any solution of the complex Monge-Ampere equation, which means that for the derivation of this formula, you must use complex Monge-Ampere equation. Now, what about gravitational instantons? These objects asymptotically look like a flat space, four-dimensional space, so the curvature is concentrated in a finite region of Riemannian space-time. But since time is also involved, the boundness of such domain means also boundness in time. So these objects arise and disappear with the time. The most important gravitational instanton is the so-called K3. Geometrically, it is the Kummer surface, and its explicit metric is still unknown, though many its properties were studied by some famous scientists, but no explicit metric. As Maciej Dunajski explained in his recent brilliant book, the name K3 is because of the three great geometers, Kummer, Keller, and Kodaira. And the metric on K3 is even more difficult to find than to climb up the difficult mountain K2 in the Karakoram range of the Himalayas. This explains somehow the terminology, the name. Now, a characteristic feature of the K3 instanton is that it does not admit any killing vectors, generators of continuous symmetries. And therefore, the metric potential should be a non-invariant solution of complex Monge-Ampere equation, because then no symmetry reduction in the number of independent variables may happen. And this is our global task is to get at least maybe some part of the K3 instanton, and one way to attempt to get it is to satisfy this necessary condition, but of course not sufficient condition of the absence of symmetry reduction. Now, about gravitational, the most well-known gravitational instantons are by Higuchi-Hansen, Taub-Natt, and multi-centered gravitational instantons by Gibbons-Hawking. All of these instantons admit at least one killing vector, one continuous symmetry, so they are not K3. A good review, for those who may be interested, a good review you may find in Physics Reports, volume 66, number 6 of 1980 by Higuchi, Gilkey, Hansen. Gravitation, gauge theories, and differential geometry. And also in the book of Dunaysky, Solitons, Instantons, and Twisters, Oxford University Press, 2010. Now, we don't want to take care all the time about the reality of our objects. Therefore, we make a transformation to real variables, after which all the objects are automatically real. This, you can see this transformation from complex to real variables. This is the notation. We introduce coefficients A, B, C. Like this, delta, capital delta is two-dimensional Laplacian in the YZ plane. And also we introduce Q, which is B squared plus C squared plus epsilon over A. And V is equal to UT. It is the second component of the unknown, and we consider our basic equations in a two-component form, because we want to start with the Hamiltonian and then even B-Hamiltonian form of the basic equations. Now, in real variables and two-component form, the complex Monge-Ampere equation becomes, like you can see here in the equation 8. We call it complex Monge-Ampere system, CMA system. Now, formula 9 gives us the metric transformed to real variables. And here we introduce the coframe of one forms, like this. Now, this is the Hamiltonian form of the CMA system. Deltas, they are closely related to variational derivatives. They are Euler-Lagrange operators, where Hamiltonians, they are functionals, integrals of H. So H1 here is Hamiltonian densities. And what is J0? It is analog of the, it determines the structure of the Poisson bracket. In one of our previous papers, we obtained the concrete form of this Hamiltonian operator. This is one. And the corresponding, also the form of the corresponding Hamiltonian density, H1. Now, we have derived there also two recursion operators. Each of the recursion operators determines a hierarchy of Hamiltonian equations like this. You act with the recursion operators on the original Hamiltonian operator Jo, and you obtain another one, J1. And we have two of them here, which serve for two hierarchies. Now, I don't want to go into some, how to say, things related to the definition of delta to the minus 1, because it involves addition of an arbitrary element of the kernel of delta. And in order to have the Hamiltonian property, the Jacobi identity for J's, it is, we should eliminate this arbitrariness by the condition such that not only delta times delta to the minus 1 is equal to 1, but also delta to the minus 1 times delta is equal to 1, where 1 is the unit operator. And we have explicitly demonstrated such a definition in one of our previous paper in 2017. But I don't want to go into these things now. Now, the flow, our original flow, can be generated not only by J1 from the Hamiltonian density H0, but also by, not only by J0 acting on H1, but also by H1 acting on H0. And this is a bi-Hamiltonian representation, which is the definition of a Hamiltonian integrable system given by Magritte. Also, since we have two different hierarchies, the same flow 11 is also generated by J1 from H0. H0 we have, low zero and higher zero. If we apply recursion operators again, we will obtain an infinite sequence of bi-Hamiltonian systems, which are called hierarchies. Now, we are interested in non-local flows, and the first non-local flows of each hierarchy, they're generated either by J sub 1 or J super 1 from the Hamiltonian H1. The concrete form is, you can see here, and for the second components, to have the equations for the second component, you must just differentiate with respect to time t. Now, why we are so interested in the non-local flows, because we want solutions invariant under non-local symmetries, which are determined by conditions that U does not depend on time tau 2 or tau 2 prime of these flows. So we obtain higher order differential constraints which should be compatible with our original equations by construction. And why we impose not just one but two invariance conditions? Because we want to keep the discrete symmetry between the two Hamiltonian structures when Z is replaced by Y and Y in its turn is replaced by minus Z. Then we must make some clever mixture of these two equations so that we obtain one much simpler equation, 25, and another one, equation 26, which are much simpler than the original invariance conditions. And here, phi and he, they are conjugate harmonic functions in variables y and z. Then we solve this system for which is linear in Vy and Vz with respect to y and z, and denoting small delta is uxv squared plus uxz squared, we obtain such result. And in the following, for simplicity, we set phi and he equal to 0 and call this case as the invariance under special first non-local symmetries. Not just first non-local symmetries, but special first non-local symmetries. Now, we introduce some quantity W, which is not obvious probably at the first sight. But the reason is that first I tried the ansatz W equal to 0. What is called here W just should vanish. But after long calculations, it leads to symmetry reduction. Therefore, instead, I introduce W not requiring it to vanish. The equations simplify in terms of W, and the two-component form of the complex Monge-Ampere equation becomes like this, the equation 30. Now, I understand that what follows, I cannot skip it completely because this is what is really done here. But of course, you may not like such details. I understand, but I don't know how to avoid it. So what follows next is some very clever use of the integrability conditions. First of all, we obtain equations 31, and the integrability conditions is the simple equation 32, and then we obtain 33, and then we obtain very simple formula 34 by differentiating the definition of W with respect to time, and it requires quite long calculations with an unexpectedly simple result, 34. Then we may impose further integrability conditions and obtain the equations for delta of u, Laplacian of u, which are first order equations which are easily solved by method of characteristics. First, you consider the combination of these equations, and its solution is delta of u is arbitrary smooth function f of ux xt. And then, using the remaining equation, you specify that this f depends only on two variables, zeta and t, where zeta is some function omega depending only on ux plus x, and omega of ux is expressed in terms of w of ux in terms of this integral. Now the equation we obtain another equation that small delta is a squared, where capital A is this guy. So that the latter equation can be rewritten in such form: uxy is a sine theta, uxz is a cosine theta, where we have introduced a new unknown theta of x, y, z, t. Now we consider integrability condition of this system, which ends up in the equation 40. And another equation, delta of u f of zeta t, results in the similar equation, 41. So we solve algebraically this system of linear equations to obtain theta y and theta z, and then integrability condition theta yz is equal to theta zy ends up in this equation below. And this is one important technical point. You see, sum of squares equals 0. But you remember that all the objects are automatically real. Therefore, the only solution to this is that each square separately is 0, which greatly simplifies the whole thing. We obtain the equation 43, and we obtain that theta x is 0, so that theta depends only on yzt. And we also obtain simplified expressions for these parameters, b tilde and a tilde. And further equation 43, where we use theta x equal to 0, implies also that theta y and theta z is 0, and therefore theta is a function of t only. Great simplifications. Then we have compact expressions for the derivatives a, y, a, z, a, x, where the last equation, if you remember what is a, then you may derive that from the last equation 47, we obtain such result. the equation on omega only, which yields the result omega prime. Prime means derivative of function of one variable. Omega depends only on ux. Omega prime is equal to 1 over C1 ux plus C2. And therefore, we obtain a compact expression for capital A, and using it, compact expressions for uxx, uxy, uxz. Also, we have simplified expressions for the derivatives of v, vy, vz, vt. With the integrability condition, '52. Now, we have two cases. If C3 prime of t is non-zero, then we can express Vx from here and consider further integrability conditions. Vyx is equal to Vxy and Vzx equals to Vxz, and this implies C1 times C3 is 0, but C1 prime is non-zero, therefore C1 cannot be 0. Because if C1 is 0, it leads immediately to symmetry reduction. Therefore, we have here C3 is 0, and this contradicts to our assumption that C3 prime of t is 0. Therefore, the correct is the opposite case, when C3 prime is 0 and C3 is constant, which gives that theta of t is linear in t, and Vx is undetermined in this stage. And all the integrability conditions for V are identically satisfied. Now we had the equations for uxy and uxz. Now we have Vy and Vz, and we differentiate both of them with respect to x to obtain these results. And we also have uxy equals something, uxz equals something. Differentiate with respect to t, and then we have vxy again, and vxz is equal to something. And the result coincides with what we already have. The only new equation we obtained differentiating the equation for uxx with respect to t, from where we get vxx. So we now have vxy, vxz, vt, and vxx. Now we consider further integrability condition. Vt exx minus vxxt equals 0, which yields such equation, 57. But this is the equation for f. But f cannot depend separately on ux and x, but only on the combination zeta, which is logarithm of c1 ux plus c2 over c1 plus x plus zeta 0. F depending only on zeta t. And therefore, this equation splits into two equations, where the one without exponential and the other one proportional to exponential. Equations 58 and 59. Now we combine them so that to simplify the equation 59 to this form. And it turns out that it's very simple to integrate it and in T and Z, and to obtain general solution in this form for F. F of T and gamma of T, at this stage, they are arbitrary smooth functions. Now we have two equations, so we input our result for F in the remaining equation, and then obtain again one result which splits into two equations containing the exponential and without the exponential term. And the resulting two equations yield the general solution that FO is 1 over mu t, where mu of t is harmonic oscillation with frequency 3 times C1, mu1, mu2 are arbitrary real constant. And the one remaining equation is this one, for the equation for gamma. It is easy to obtain its two Lie point symmetries. And as it was shown by Hans Stephanie in his brilliant book on differential equations and their symmetries, who showed that any second order equation admitting two Lie point symmetries can be integrated in quadratures, and he gives also algorithms for each of the four different cases. So I just used this result.
I'm sorry, it is the result by Sophus Lie much earlier than Stefan.
Sorry, say this again.
This is the result by Sophus Lie, not by Stephanie.
No, yes. But he also says in the introduction that he got his knowledge from the original works of Sophus Lie. But I mean, I'm not sure that Sophus Lie, I didn't read his original works. But I think that at least Stephanie presented in the results in such a readable form that he specified algorithms very precisely, algorithms for the integration. But of course, you are right. This is a Lie theory, of course. Therefore, I said Lie symmetries, not Stephanie symmetries. Okay, so using our result, we obtain the final result in this form. Yes, and also I forgot to say that gamma, the solution is gamma is nu over mu, where nu is harmonic oscillation with the frequency 2C1. And this is the result for F. Or if we don't want zeta, we can come back to the original variable x to have it in this form. Both forms are useful. Now, if you remember, we have the equation, second order equation, uxx is equal to something. We can easily integrate it with respect to x with the following result, where we introduced a new function gamma, capital gamma, which you can see the expression 69, and here sigma of yzt is the constant of integration with respect to x. And then we use this in the formula for f, where you can see ux. So we use this ux from here, and we obtain that. Here I remind our different notation. A, which is delta of u, which is f, it is minus or plus gamma to the power minus 1/2. And then ux from here is also expressed in terms of a, so that we have more compact expression than if we try to express it in terms of gamma. Then we use this result in the second and third equations in 50. What is 50? Let me see. It is uxy and uxz we also have. So we obtain from there the expressions for gamma y and gamma z in terms of sigma y and sigma z, and we obtain sigma y and sigma z from there, and integrating we obtain sigma c1 c3 y sine theta plus z cosine theta plus sigma O of t. And this result should be used in the definition of gamma. Now, we have ux, so we may consider the derivative, time derivative of it to get vx, also very compact form. Now, also, since we have ux, we can integrate the expression with respect to x to get u with another constant of integration rho depending on y, z, t. And some things we know about this rho. The unknown things are rho O of t, constant of integration, and r of yz. But what we know that r of yz is a harmonic function. Now, differentiate this expression for u, we obtain v as ut, like this. And next, we can further differentiate this v to get vt, because we have also vt used in our equations, complex Monge-Ampere system in the real two-component form, where I remind what are A, B, C here, and what is Q. And after, when we plug in our results for V and U, VT, UT, and so on into this system, after many cancellations and quite lengthy calculations, we obtain a simple equation for rho O of t with two primes, which we can integrate with such result. And sigma O here also is a function of t only, which satisfies this equation. And the solution is this one. Also very simply integrated. Now, we can formulate our main result. So we got new unknown solution to the complex Monge-Ampere equation. here it is in two-component form, but of course we can always rewrite it in a one-component form and come back to original complex variables, which I don't do. And here I remind what is A and capital gamma. And we know what are nu, mu, and gamma. We know what is theta, and a lot of constants are involved, which are arbitrary real constants. And the main results we formulate is a theorem. The expressions for u and v provide the solution of the complex Monge-Ampere equation in its real two-component form. This solution, by construction, is invariant under the first non-local symmetry flow of the complex Monge-Ampere equation in each of the two hierarchies of this equation. With the generic set of constants, this solution is non-invariant under point symmetries of complex Monge-Ampere equation, and consequently, it experiences no reduction in the number of independent variables. What do I mean by the generic set of constants? I mean that checking the non-invariance of the solution, I will show you a little bit later how to do it. You may find some special values of constants in our solution when you will find some symmetries. But generic set means that you cannot impose any constraints on the parameters of our solution, and in that case all the symmetries will vanish, so no symmetries are point symmetries are admissible. Now the non-invariance of the solution under point symmetries is obvious from the absence of symmetry reduction in the solution, because it depends on 4 independent combinations on variables t, x, y, z, not 3 or less of them. You may see that you have, for y and z, you have 2 different combinations of them, which enter the expressions for u and for v. And therefore, there is no reduction in y and z, and obviously no reduction in x and t. And non-invariance of the solution for the Keller potential of the metric implies the absence of point symmetries, killing vectors, for the metric itself. Because if the potential of the metric depends on 4 independent variables, then its derivatives, partial derivatives, also will depend on 4 independent variables. And you can see it explicitly looking at the metric coefficients which follow further. And as far as I know, there are no published examples of non-invariant solutions of complex Monge-Ampere equations, and also of the corresponding gravitational metrics with no killing vectors. The only exception is our earlier paper, which I will give you a little later. I'll give you a reference together with Andrei Malekh, published in Sigma, where we tried different approaches to this problem, but there we used just most obvious solution of the equations taken out by chance. And therefore, it's not surprising that the result is not what we wanted. No instanton behavior. So right now we can claim that there is still no progress in the explicit construction of K3 instanton metric. Now, how looks the metric looks? This is D squared metric coefficients are Q, A, B, C. We can further simplify it introducing the coframe of one forms when our metric takes the diagonal quadratic form, where for epsilon plus or minus 1 we have either Euclidean or neutral signature. I think it's worth mentioning that these are general results, not related to our particular solution. So if you find any other solution, you can use these ready formulas immediately to obtain the metric and metric coefficients. For our solution, these are the explicit formulas for A, B, C, and Q. So the result is quite complicated. This is again about reduction. Thus, we claim that we have obtained the Ricci-flat anti or maybe just self-dual metric without killing vectors. It is generated by a non-invariant solution of the complex Monge-Ampere equation determined only by its invariance under the pair of special first non-local symmetries of CMA without any additional assumptions. So this is not a solution of CMA taken out by chance, but very special solution. Such an invariance does not lead to a reduction in the number of independent variables in the solution, as opposed to the invariance under Lie point symmetries. The metric has a rather complicated form, and further analysis is needed to study its other properties, such as singularities, asymptotic behavior, and the key property if it is defines compact manifold or not, because K3 is compact. Thus, at this stage, we can by no means claim that our metric belongs to K3 instanton. However, what we have demonstrated, it is how invariance under non-local symmetries can be used in the attempts for constructing K3. Also, this method can serve as a direct approach for obtaining non-invariant solutions of CMA from the invariance under other non-local flows in the hierarchy. We have used just the first members. Now, I do not present this result here because it's quite, takes space and time and complicated. That for the Euclidean signature, we have explicitly calculated Levi-Civita connection and Riemann curvature for any metric of this form which I have demonstrated. And therefore, for future researchers, it may be very useful. Because again, if you find a new solution of complex Monge-Ampere equation, then you just use this solution in these formulas, and you immediately obtain connection and Riemann curvature. Now, what is the rigorous way to check the non-invariance of the solutions? First, you easily calculate Lie point symmetries of this equation in the two-component form. We have 8 generators and also infinite subalgebra also, where alpha and beta are harmonic functions in Tx and Yz. Then what you do, you take a linear combination of all symmetry generators with arbitrary constant coefficients and impose the condition of the invariance of the solution of the complex Monge-Ampere equation, where U is some f, some solution, V is its time derivative. And the invariance condition means that X acting on the column f of t minus column uv taken on solutions u equals f and v equals ft should be 0. You can check that the simpler equation you get from the first row of this equation, and the second row is just time derivative of the equation in the first row. And this first row looks like this. What you do, it's quite a complicated calculation. You take our solution, f, use it here, and try to satisfy it by the choice of coefficients in the symmetry generator, C3, C5, C6, and so on. But not using any restrictions on the parameters of our solution. And then you get the result that all coefficients, C1, C2, and so on, C8, they should vanish to satisfy this invariance condition, and which means that the whole X vanishes. There is no symmetry of our solution for the generic set of constants. Now, of course, you may ask how non-zero solutions for the constants may happen for special values of our solution parameters. This would mean that such special solutions, particular cases of our solutions, are invariant. The full analysis of this situation is very lengthy and complicated and deserves a separate study. Now, what is the summary? We have demonstrated that the general requirement of invariance under non-local symmetries of CMA yields non-invariant solutions under any point symmetries. We have obtained the most general form of the solution of CMA, which is invariant under the special first non-local symmetry in each hierarchy of CMA, not just a solution taken out by chance. And we have also presented the corresponding anti-self-dual Ricci-flat metric without killing vectors. Much more details of this work you can find in my preprint with the same title, which was published in Archive on 5th of October this year. The bi-Hamiltonian structure of the complex Monge-Ampere equation was discovered by us. This is the list of forces very long ago in 2008. And this is the reference to my work with Malich, where we get anti-self-dual Ricci-flat matrix without killing vectors, but unfortunately not an instanton metric and also some singularities and so on. So thank you very much for your attention.
Thank you very much. Well, comments, questions are welcome. Yeah, Oleg. Switch on microphone.
So sorry. You listen me. My question is the following. It is about the Hamiltonian system. I just want to understand. As I remember, system is Hamiltonian if there are two Hamiltonians, but there is a second condition of compatibility of Poisson brackets. So in your case, you have Hamiltonian system in the strong meaning or in the weak meaning?
I don't know if you call it strong or weak, but what I know is that two basic properties of the Hamiltonian operator are satisfied. It is skew-symmetric, first of all, and the second is the Jacobi identity is satisfied.
Jacobi identity for pencil of Poisson brackets, or just, no.
For the Hamiltonian operator, J, which fixes the structure of the Poisson. But yes, it is the same. Yes.
Okay, thank you.
Yes.
Thank you.
More questions? Remark? Oleg? Oleg, microphone.
Mikhail Borisovich, Oleg Morozov. The question is the following. What about contact symmetries of your equation? Did you check invariance or non-invariance with respect to the contact symmetries? The Lie algebra of contact symmetries is, for this equation, is much bigger than the Lie algebra of point symmetries. Perhaps your solutions are invariant with respect to contact symmetries.
No, I did not check, but also don't forget that we are interested in the symmetries of the metric. And contact symmetries, they involve also the unknown function as independent variable.
Okay.
So I didn't check, but I doubt very much that it may give anything interesting.
Okay. Thank you very much.
Thank you. More questions? More remarks? Okay, thank you very much for your very interesting talk. So visit our seminar, do not forget about us. So we'll meet next time in a week, at the same time, 9:20. past 7 in the evening. Okay, see you. Thanks for visiting the seminar.
Thank you
Goodbye.
for your invitation
Yeah,
again.
you're welcome. You're always welcome.
Bye-bye.